Sorry about that, guys. My battery died. So let's kind of back up and let me remind you where I was. When we talk about the molarity of the solution, okay, the 0.150 molar NaOH. What that means is I have 0.150 moles of HNO3 for every 1 liter of solution. Now, that's a conversion factor. It's a ratio between two things. I can flip that upside down if I need to. So right here, I can write 1 liter over 0.150 moles of HNO3. So notice moles and moles of HNO3 divide out, and I'm left in liters. So 0.0350 times 0.108 times 2 divided by 0.150. That gives me 0.0504 liters. Now I wanted an answer in milliliters, so 0.0504 liters times 1,000 milliliters for every 1 liter. Liters and liters divide out. I get a final answer here. Okay? I'm running out of room. Our final answer is 50.4 liters of the HNO3 solution. And that's a reaction stoichiometry problem. And guys, if you don't want to string this out like this, break it up into little manageable chunks. Break it up into steps. Do a conversion from milliliters to liters. And then use the molarity equation to go from volume of A to moles of A. Then use stoichiometry to go from moles of A to moles of B, and then do the rearrangement of the molarity equation to go from moles of B to volume of B. I like to string it out kind of in one long string, but you don't have to. Problem solving is finding out what works for you. So pick out the pattern that's going to work for you. Okay? All right. Now, you can also ask me questions in lab and we can go over example problems. All right, I'll take time to do that. Now, we're going to let our calculators cool off and we're going to talk about solution formation, okay, and the nature of water. Now, water is our most common solvent. Salts dissolve up in water, a lot of covalent compounds dissolve up in water. Water is often referred to as the universal solvent. So what makes water the universal solvent? Okay? What gives it this magical set of properties? Well, let's talk about things we know about water. We know that water is very small and it's a very polar molecule. Okay? So when we look at water, thinking about its bent molecular geometry and the fact that it contains two very polar bonds, we end up with a molecule that is overall polar. The oxygen end of the molecule is slightly negatively charged. The hydrogen side of the molecule, okay, is slightly positively charged. Remember up here on this end, we have those two lone pairs in the valence of oxygen that are sticking out like this, kind of perpendicular to the board, okay? One set's behind the board, one set's up here. So being very small and very polar allows oxygen to do things like interact very strongly with cations and anions. So when ionic compounds dissolve up in water, something like sodium chloride, the sodium is going to have an interaction with the negative end of the water molecule. And then there's the, of course, ionic bond between the sodium ion and the chloride ion. And then we have an interaction between the chloride ion and the positive side of the water molecule, because water molecule is polar. Now, there's a battle going on. This interaction versus this interaction versus this interaction. Sodium looks and says, I can have an interaction with water molecules, or I can have an interaction with chlorides. Chloride says, I can have an interaction with sodium ions, or I can have an interaction with water. And it has to decide which one's stronger and which one's better. Remember, nature is all about energy relationships and strength of interactions. Turns out for sodium chloride, and we'll talk about this in more detail next semester, that it can have a really good interaction with water. Sodium ions, chloride ions, great interactions with water. And so sodium gives up its interaction with chlorine. The chloride ion gives up its interaction with the sodium ion to dissolve up in water. And when a sodium ion dissolves up in water, it surrounds itself by 6 water molecules, okay, with all of the oxygen ends pointing in. Chlorine gets an entourage of 6 water molecules also, with the hydrogens moving in. Now, the big kind of kicker bonus for sodium chloride is when it dissolves up in water, now the sodium ions and chloride ions are free to move around. In the solid, they're locked into position. That's going to be critical when we talk about this next semester. Now, when an ionic compound dissolves up in water, since the ions are now free to move around, that solution can conduct electricity. And that means that the sodium chloride can be classified as an electrolyte. An electrolyte is a substance that, when dissolved in water, produces free ions in solution and allows the solution to conduct electricity. So salts that dissolve up in water are called electrolytes. Okay? Acids, when they dissolve up in water, are also electrolytes because of the reaction that they have with water. Non-electrolytes are substances that, when dissolved in water, do not produce free ions in solution, and the solution will not conduct electricity. Sugars, when dissolved up in water, they dissolve up through a different process, and they don't produce ions in solution. Okay? Very different than what a salt does. So let's look at an example here. Okay, here is a sucrose molecule, and it's interacting with water. The solute sucrose interaction with water is called an intermolecular force. Inter meaning between molecules. Okay? Notice that in some places it's the oxygen end that's interacting. Okay, some places it's the hydrogen end. Red stands for oxygens, white stand for hydrogens, the black in here, they're carbons. This is a very polar molecule, and water can do something called hydrogen bonding. And in hydrogen bonding, a lone pair of electrons on an oxygen is strongly interacting with a hydrogen on another molecule that's bound to an oxygen, nitrogen, or fluorine. Okay? And this is a site-specific interaction. On something like sucrose, notice there are lots of oxygens bonded to hydrogens, or better if I said a lot of hydrogens bonded to oxygens. So there's a lot of sites where I have lone pairs of electrons on oxygens and I have hydrogens bonded to oxygens for water to interact with. Okay? So glucose dissolves up in water through a hydrogen bonding interaction. So it's an interaction between a hydrogen on one molecule bonded to an oxygen, nitrogen, or a fluorine to a lone pair of electrons on another molecule that has a nitrogen, oxygen, or fluorine. Okay? So when the sugar molecules dissolve up, they stay intact in water. They don't produce any ions. They were a covalent molecule to begin with, and they stay intact and whole as an uncharged covalent molecule in water. So the attractions between the sugar molecules and the water molecules overcome the attraction of sugar molecule for sugar molecule, and they dissolve up. Now, I mentioned it earlier, our special class of covalent compounds, the acids. Okay? What happens with acids is that acids, once they dissolve in water, actually chemically react with water to produce hydronium ions and an anion. So if HCl dissolves up in water, it then reacts with water to produce hydronium ions and chloride ions. Acids then are electrolytes. Strong acids 100% ionize in water. That means that every HCl molecule that becomes aqueous reacts with an HCl to produce hydronium ions and chloride ions. This reaction goes to what we refer to as completion. In a blink of the eye, there's no true HCl molecules left in the solution. We only have hydronium ions and chloride ions. 100%. Now, weak acids do not 100% ionize in water. Okay? HF is an example of a weak acid. When it reacts with water, notice the double arrow, I get hydronium ions and fluoride ions, but I'm going to have some intact HF in solution. Now, that is still an electrolyte because there is some production of ions when HF is dissolved up in water. So no matter if you're a strong acid or you're a weak acid, you're an electrolyte. Okay? All right. Reactions. Guys, if we look at reactions, there are thousands and thousands and thousands and thousands of reactions. And when you take organic chemistry, you're going to be looking at lots and lots of categories of organic reactions. Right here, what we're going to do is look at kind of some of the basic first pass at reactions, okay, and how we categorize reactions. First thing we do when we have a reaction, we can talk about it being a non-redox reaction or a redox reaction. Don't worry, I'm going to define redox for you in a minute. Non-redox reactions can be broken down into double replacement reactions, combination reactions, or decomposition reactions. Double replacement reactions can be further broken down into precipitation reactions or acid-base reactions. Redox reactions can be broken down into single replacement reactions, combination reactions, decomposition reactions, or combustion reactions. To be able to understand what a non-redox reaction is, of course, we first need to define what a redox reaction is. So redox, what is it? A redox reaction is one in which electrons are transferred over the course of the reaction. We think of redox as a two-step process. Oxidation, which is the loss of an electron, that's a give-up part, and a reduction, which is the gain in electrons, which is the take-in part. You cannot, I repeat, you cannot have oxidation without reduction, and you cannot have reduction without oxidation. Okay? So let's look at a really simple reaction. lithium plus chlorine going to lithium ion plus the chloride ion to make lithium chloride. So lithium goes to the lithium ion. It has to give up an electron. That's oxidation. Chlorine took in an ion to become an electron to become the chloride ion. That's reduction. So when the lithium reacts with chlorine, it's a redox reaction, and the lithium undergoes oxidation and the chlorine undergoes reduction. Okay? So anytime we have a reaction between a metal and a nonmetal, it is a very obvious redox reaction. And it's easy to decide who's oxidized, who's undergoing oxidation, who's undergoing reduction. The metal is always going to undergo oxidation. The nonmetal is always going to undergo reduction. But sometimes it's not so clear. We might be reacting two covalent compounds together, and there aren't ions formed, so we need to be able to determine if oxidation and reduction is going on. So we're going to need something called an oxidation number. Now guys, this is a bookkeeping tool, and it's used to monitor whether an atom is losing electrons or gaining electrons. Or you could think losing electron control, gaining electron control. The oxidation number is the charge an atom would have if the electrons were not shared in a chemical bond, but were always transferred completely to the most electronegative element in the bond. So to assign oxidation numbers, we're going to need some rules. In your book, the rules for assigning oxidation numbers are on page 343. Don't panic, I'm not going to ask you to memorize these on a test. I'll give you the chart. Now, here's one from a different textbook. I like this one a little better. The one in your book is using the same process, it's just laid out a little differently. Okay? So let's go over the general rules. For an atom in its elemental form, sodium, oxygen, chlorine, pure element, oxidation number is always 0. For a monatomic ion, the oxidation number always equals the charge of the ion. The sum of the oxidation number values for the atoms in a molecule or a formula unit of a compound always have to add up to be 0. The sum of the oxidation number values for atoms in a polyatomic ion have to sum up to the charge on the ion. So if I have a nitrate ion which has a charge of -1, the sum of the oxidation numbers for the oxygens and nitrogens in nitrate ion have to add up to -1. Now specific rules. All group 1A, that's the alkali metals, always have an oxidation number of +1 in a compound because they only form ionic compounds where the alkali metal is going to have a 1+ charge. For group 2, the oxidation number is always going to be 2+, same reason. Hydrogen is going to have an oxidation number of +1 when it's combined with a nonmetal, and -1 when combined with metals and boron. Okay? Fluorine always has an oxidation number of -1 in all compounds. Fluorine is the most electronegative element on the periodic table. And because it's the most electronegative element on the periodic table, anytime it gets involved in bonding, it wins the battle for electrons. Oxygen has an oxidation number of -1 in peroxides. In a peroxide, you have an oxygen single bonded to an oxygen, and then each oxygen is either covalently bonded to something like a hydrogen, or it's ionically interacting with something like sodium, but that's why it's -1, okay? The oxidation number for oxygen and all other compounds is -2, except when bonded to fluorine. And then it gets a funky oxidation number of +2, okay? And lastly, group 7A, that's the halogens, have an oxidation number of -1 when combined with metals and nonmetals, except for oxygen, okay? If oxygen bonds with anybody else in the halogen family below fluorine, oxygen gets an oxidation number of -2, and they're going to end up with a positive oxidation number. Also, there's a pecking order. Remember, electronegativity decreases as you go down the family. Fluorine is at the top. With fluorine's bonded with chlorine, fluorine is going to have a -1 oxidation number, chlorine ends up with +1. If fluorine were to bind with iodine, fluorine's going to be -1, iodine's going to end up being +1. If chlorine were to bond with iodine, chlorine's more electronegative, it gets the -1, iodine gets stuck with +1. Poor iodine has such a hard life. Okay? So we're going to look at some compounds, and we're going to assign oxidation numbers. Now hopefully you've printed out your notes so that those oxidation number rules are sitting right beside you, okay, as we do these. All right. So first one here, sulfur dioxide. Okay, the oxidation number for oxygen is -2. The oxidation number for sulfur is not covered by any of the specific rules, so I'm going to have to calculate it. So I can say that the oxidation number for sulfur plus 2 times the oxidation number for oxygen has to add up to be 0. So the oxidation number for sulfur plus 2 times a -2 has to be 0. So I can say here that the oxidation number for sulfur has to be +4. Okay, not bad. All right, let's try another one. Okay, I'm going to use carbon. We're going to look at CH4, CO, and CCl4. Okay, 3 situations, 3 compounds where we have carbon. Now, the oxidation number for hydrogen is covered by the specific rules. Hydrogen's bonded to a nonmetal, so it has an oxidation number of +1. Okay, the oxidation number of carbon here, though, is not covered by any of the rules. So, the oxidation number for carbon plus 4 times a +1, which is the oxidation number for hydrogen, has to sum up for 0. The oxidation number of carbon here then is -4. In carbon monoxide, the oxidation number for oxygen is covered by the specific rules. It's -2. The oxidation number of carbon isn't. We're going to have to calculate it. So the oxidation number for carbon plus 1 times a -2 has to add up to be 0. So the oxidation number of carbon here is +2. So notice here in 2 different compounds, carbon has 2 different oxidation numbers. Lastly, okay, the oxidation number for chlorine here in carbon tetrachloride is -1 because it's a halogen and it's not bonded to oxygen or another halogen. The oxidation number for carbon, we don't know. So the oxidation number for carbon plus 4 times a -1 equals 0. So the oxidation number for carbon here has to be +4. The oxidation number for carbon in a compound can vary anywhere from -4 to +4, and yes, it could have an oxidation number of 0. Okay, so that's how we calculate oxidation numbers. Okay, so we can calculate oxidation numbers. What good does it do us? By tracking oxidation numbers, we can discover which element in a reaction is undergoing oxidation and which element in a reaction is undergoing reduction, and if oxidation reduction is happening at all. If the oxidation number for an element goes up as we move from the reactant side to the product side, the element underwent oxidation. It lost electrons. If the oxidation number goes down, for an element as we move from reactant side to product side, reduction has occurred, which means gained electrons. So we're going to look at some problems and look at whether oxidation has happened, and what's undergoing reduction. So 352. And we're going to look at a couple of reactions here. Okay. 4 aluminums plus 3 oxygens going to 2 aluminum oxides, and a calcium oxide plus carbon dioxide going to calcium carbonate, and well, let's just do these 2. Okay? Aluminum here is pure. Its oxidation number is 0. Now we write oxidation numbers directly above the element, okay? Oxygen here has an oxidation number of 0. Remember, we put charges as a superscript behind the symbol of the element. Oxidation numbers go as a representation right above the element. Now here I have an ionic compound. Oxygen is bonded to a metal. Its oxidation number is -2. Aluminum is bonded to a non-metal. It's an ionic compound, is +3. So notice aluminum went from 0 to +1, so that's the loss of electrons. That's oxidation. Oxygen went from 0 to -2, so it gained electrons. That's reduction. Now, the word reduction comes from the fact that we reduced the oxidation number. The oxidation number went down. 0 to -2 is reduction. The word oxidation comes from the fact that when oxygen reacts with almost everything, it takes electrons from it, and it causes it to lose electrons. So the word oxidation means that oxygen's going to take your electrons. Okay? Let's look at this second one. Here I have calcium oxide. It's an ionic compound. Oxygen is a -2 ion there. Calcium is +2. Now, when you're writing oxidation numbers, notice that the sign of the charge is written in front. If it's the ionic charge, the sign of the charge is written in back. Oxygen here is -2 by oxidation numbers. Carbon here is +4. Okay? Now, over here I have calcium, which is +2, oxygen, which is -2. So I have 1 times a +2 plus 3 times a -2 plus the oxidation number for carbon having to add up to be 0. So that's -6 plus 2, so I've got -4 plus the oxidation number of carbon being 0. Carbon here is +4. So notice, calcium is +2 on both sides, oxygen's -2 on both sides, carbon is +4 on both sides. Nothing changed oxidation number. That means that this is a non-redox reaction. So we have a redox example and we have a non-redox example. Now, a couple of more terms that we need to throw in when we're talking about redox chemistry. Okay? We're going to use the term oxidizing agent and reducing agent. Oxidizing agent is a reactant that causes oxidation and therefore is a reactant that contains the element that is reduced. The reducing agent causes reduction and therefore is the reactant that contains the element that is oxidized. Now, let's look at our redox example here. Okay, aluminum underwent oxidation. So aluminum here is our reducing agent. And oxygen is our oxidizing. Okay, it causes the other guy to be oxidized. Now, let's look at a reaction that doesn't involve just pure elements as our reactants. Okay, so I'm going to look at the reaction 5 carbon dioxides plus an I2O5 going to iodine and 5 CO2s. Now, iodine here is pure, its oxidation number is 0. We've already played carbon dioxide, oxygen is -2, carbon is +4. This is carbon monoxide. Carbon here is oxygen is -2, carbon is +2. Now here, oxygen is -5. If I take 5 times -2, that's -10. There's 2 of these. Iodine ends up as +5. Guys, you can write these out, but I'm just trying to get to work things through to show you oxidizing, reducing agents. Notice oxygen is -2 everywhere. It doesn't change oxidation number, so it's not oxidizing, it's not reducing. But notice that carbon goes from +2 to +4. So that's oxidation. Okay? Carbon undergoes oxidation. Iodine goes from +5 to 0. That's reduction, because it had to gain electrons to do that. So our oxidizing agent has to be the I2O5, diiodine pentaoxide, because it contained the element that underwent reduction. And our reducing agent is the carbon monoxide, because it contained the element that underwent oxidation. Every redox reaction is going to have an oxidizing agent and a reducing agent, and they're both reactants. Okay? So you can't have oxidation without reduction. You can't have reduction without oxidation. You're always in a redox reaction going to have an oxidizing agent and a reducing agent. Okay? Now, this is a good place for me to stop. Okay, process all of this, and this is where we'll pick up in the next lecture, talking about combination reactions. Let's sign off.